We have walls that we may call retaining walls. I'm not sure if you guys hear about this term before, but it is widely used. You can see very small retaining walls versus large size retaining walls. I mean, it depends. And also we have walls that we call shear walls. This is going to be very similar to the wood shear walls that you see in houses and wood construction, but this is going to be in larger scale and used in big buildings. And we have also walls that you can call here basement walls or gravity walls. Let me show you here for quick. This is going to be here reinforced concrete shear wall. So here's a concrete wall. Now, I cannot call this a column because look at the column. The column is kind of a square or maybe rectangular, but the aspect ratio, which means the length to the width ratio, has a maximum value of, let's say, 2.5 to 3, which means the length of the column is going to be maybe maximum 2.5 times the width of it. But in walls here, you see the wall is really long, and this wall, the thickness of it was 16 inch, and look at the length. So the aspect ratio here for the cross section for the wall is much larger than that for just a column. A column is going to be a maximum of 2.5. So when the column is going to start to get longer, like you see this column here in the back, see this one? You may call this a wall because the aspect ratio. So the column is actually looks like a wall, but the aspect ratio is much smaller. And if you think here about the design equations that we use for the axial load capacity, because you know this wall here, I'm sure that is also exposed to vertical loads besides some lateral loads. Vertical loads, this is what you call here gravity loads. This includes dead load and life load. So dead load and life load, we call gravity loads. So the same equation that we use for columns. You guys remember the equation for columns? Anyone recalls the equation, how it looks like? Yes, no?
You mean with low eccentricity?
Like this equation. Yeah. But this is going to be for a spiral column. This is going to be the small eccentricity, correct? This equation here, you still can use it for walls. Because this is for a structural member exposed to vertical load, axial load, right? So you have the cross-section area of the concrete, the cross-section area, and then you subtract AST. AST is going to be the vertical rebars, not the horizontal ones. Then you have F sub Y, and you have the same phi factor. And you see, also for shear walls, you can have the interaction diagram. Just in case if you forgot the interaction diagram, this is the one that you have seen in your midterm, right? You're gonna say, this is gonna be your interaction diagram, which is this one, or this one. So actually you can develop an interaction diagram for a shear wall, or for a wall, generally speaking, for any concrete wall. You can do the same thing. You put the model, you're gonna pick here the wall instead of having it to be like a square or a small rectangle with a small aspect ratio. You can have something similar to this. Look at this one here. We call this gonna be shear wall. This length is gonna be much larger than the width of it. So the thickness here, or the width, the thickness, I'm gonna call it here the wall thickness. Let's say it goes from 12 inches maybe to 24 inches in some cases. So you go maybe 12, 14, 16, 18, maybe 20 inches, maybe 24 inch. And for the length, usually we don't go smaller than, you can see here, maybe 16 feet or something, and goes up to maybe 30 feet or maybe even 100 feet, depends on the building.
Professor?
Yes.
You mentioned that formula for the spiral column. Would we use the exact formula?
No,
or
use the other one for
different
tight
reduction
columns.
factor?
You use the one for tight columns, right?
Thank you.
This is the one that was close to me at the time when I talked about it. So what I'm trying to say is this is just a regular structural member, right? Like any other concrete members. And this is going to be exposed here to some axial load, right? So if you just have an axial load, you can just use this formula for the small eccentricity, but of course it's going to be for the tight column. And in this case, you come here to the wall, right? And then you look at all of the 3 bars, the vertical, because this is a section like this. You see this? A section looking down. So you look here at all the rebars. You count all the cross-section area of the rebars. You just add them up together and then use them in your equation. And you should be fine. This gives you the axial load capacity of the wall. And you're going to see is really big compared to a column because the cross-section area is just extended, right? But sometimes these walls are also exposed to lateral forces coming from the seismic. So for example, you come here, they say earthquake forces going to be coming this way, and maybe also in this level is going to be coming this way, right? This creates a moment because the system here, the structure system is like a cantilever system. You see this? Just consider it to be like a cantilever system, if you like to model it. So this is going to be fixed here at the bottom. Total moment is going to be equal to this force times this height, plus this force times that height. You're going to have a good moment here. The moment is going to be big when it comes to concrete shear walls, and the moment is going to be acting this way, which means causing here compression and causing here tension. Now you start to put the reinforcing, and for that, when you have this lateral force, which means moment and axial load, you're going to say, okay, now this reminds me with the interaction diagram. I'm going to say, okay, now I guess I should be able to do here interaction diagram, because what's the interaction diagram for? It's going to be for a concrete member exposed to axial load, whether it's going to be tension or compression, right? And moment. So you have combination of moment and axial load. Same thing here. You see this wall exposed to axial load and moment. So you can do the interaction diagram with the software. And when you do this, you need to model, or you need to use all the reinforcing bars that you have. I can go here quick through this and explain what you're looking at. If you look here at the end, it says 8 number 8. So you have 8 number 8 on each side of the wall. Look at this. This gives you the 8 number 8. We call this jambars or boundary. This is going to be the boundary section, right, of the wall. And in here, as you see, we put lots of ties. And this ties for confinement. If you recall this, you can say this ties that we put here is going to be for confinement. We call this also ties confinement reinforcement that we put at the boundary end. Or as you see here, it's called jambars, because this is going to be the end of the wall. So at each end here, we're going to have 8 number 8. And in the middle, I have vertical rebars. Now, where's the vertical rebars? We can say vertical rebars can be going like this. I mean, just put this aside. You see this rebar goes all the way down. And it says here, number 6 at 16 inch. So number 6 at 16 inch in center. This give you the rebar spacing. And as it says here, it says each way, each face. What does it mean by each way? Each way meaning horizontal and vertical. And each face, which means that you're going to have here 2 layers. One side is going to be here, and here's the other side. Now you can figure out the amount of vertical reinforcement that you have here if you like to model this and figure out or do the interaction diagram for it. This is going to be extremely tough if you want to do it by hand because you have lots of rebars. Now, how would you do the analysis, right? So in this case, you just use a software. You have lots of software that can do this for you and give you this interaction diagram. And actually, if you look at give me a second here. I want to bring back the interaction diagram. This is an output from one of the software that we use, the PCA column software. Maybe you guys, some of you heard about it. But what you need to do is just put this model. You put this dimensions, 24 inch by 24 inch, and then you put the reinforcement bars. And you just run the model. And the model is going to be developing this interaction diagram for you. So actually, you do the same thing with the wall. Instead of having just one column, you're going to put the entire wall. Whenever you have lots of reinforcing, you put it. Whenever you have different sizes of rebar, you just put it in the location and according to the spacing, and then you run the model, you'll get a very similar interaction diagram like this. And then you look here at the amount of moment that you have at the bottom of the wall and the total axial load, and then you do this load combination and see if you're going to be within the envelope or out of the envelope. If you're out of the envelope, it means that maybe you need to add some reinforcing, or maybe the wall thickness is not enough and the wall length is not enough. If the load combinations, including moment and some vertical load, is going to be within this envelope, within this diagram, then your wall is good. You don't really need to do anything to it. And this is how you check the trends of the wall. Now, going here to our slide set 17, this is the one that you're supposed to talk about today. Here's some sample of concrete walls. Also, you can have this transparent concrete if you like. Not very common, but maybe for some architectural reason you can do it. So when it comes to the type of loads, if you imagine that this here is going to be the wall, this is going to be the vertical direction, the type of loads that you may have your wall exposed to is going to be an axial load, like dead load and life load. You can have also this what you call implant shear, and implant shear here is going to happen when you have seismic forces. So this is going to be mainly due to seismic forces. And also you have outplant shear, also due to seismic forces. And also you have the self weight of the wall itself, because the self weight is considerable weight here. When you think about the wall, the size of it, the thickness and the length, you see here that the self weight is really something that you should not ignore. Maybe in columns, you're going to say for a column 24 inch by 24 inch, the height is going to be maybe 10 feet. What weight are you talking about? It's going to be maybe less than a kip or something. But in here, the wall is going to be long wall. Maybe the length is 50 feet and the thickness maybe 18 inch and the height maybe 14 feet or so. So this weight should not be ignored. You really need to figure it out when you're doing your analysis. If the wall is exposed only or mainly to axial load, this axial force or axial load, which is gravity loads, like what? Like dead load and life load. In this case, we call it gravity wall. So what's the gravity wall? It's a wall that resists, concrete wall resist mainly is going to be gravity forces. The other type of walls, which we call here a shear wall, is going to be mainly designed, and we put it in this place to resist lateral forces like seismic forces. So in this case, we call it shear wall. You can go back here one slide. Now to go through this, it says that we have two types of walls. We have gravity reinforced concrete shear walls, and we have reinforced concrete shear walls. So we have just gravity reinforced concrete walls. Now it's going to be mainly designed to resist gravity loads, and this one's going to be mainly designed to resist, you can say here, earthquake forces. So we're going to say for gravity loads mainly, right? And this wall here is going to be seismic forces. Like earthquake, right? Which is earthquake force. Now, when you open the code and you go through it, you don't see the word shear wall and you don't see the word here gravity wall. But in here, we have this definition for them. And instead, you're going to see the term structural wall. So when you open the code itself, it says structural wall, and that's it. But they have different design provisions. When the wall is mainly designed for gravity loads, they're going to take you to a certain route. If it's going to be designed mainly for seismic forces, it goes different route. But in the code, they just call it structural wall. But if you talk to any engineer, and if you are practicing engineering, or you talk to anyone who's building a good size structure like a contractor, he just call it gravity wall or just call it a wall. And this one, he's gonna call it a shear wall. You see, guys, the difference? There is also this basement wall, like a retaining wall. What's the retaining wall? I'm gonna bring it out of the slide set that we are not planning to cover today. Here's the retaining wall. You have some soil, and you need to have something here like a stem or a wall to retain this soil in place. So this is why this is gonna be, what's the action? It is retaining the soil. So I'm gonna be calling it a retaining wall because it's retained that. This type here is cantilever system, right? This type here is gonna be, let's say, in a bridge or something, or you have a first floor. You see, this is gonna be within the building, right? So this is a basement. So you're gonna be standing here, right? And the soil is gonna be out there. Now, this wall is also a retaining wall. It is retaining the soil, and also at the same time, you may call it a basement wall. So the job or the function of having this wall here is just to resist the soil pressure. We have a previous slide, I guess that was in the introduction, slide set number 1, I believe. And I guess we're talking about type of walls, if I'm not mistaken. Was it here? Anyone recalls the one that shows 3D of a building? Okay, it's right here. This is the one. So this wall here, I mean, the term foundation wall is not used. You don't hear it unless you have a very short wall. But this one here is actually a basement wall. So I like this call out. This is what we use. So this wall here, it retains all the soil, right? But it is restrained at the top. So if the soil pressure is pushing it, if the soil pressure is pushing from this side to this side, right, it's going to be pushing to inside. It's going to be outside of the building. It's going to be inside of the building. And the soil pressure, as you guys know, is going to be modeled as maybe this hydrostatic pressure, right? I don't know if you guys have seen this or not, but we're going to be going through it. So in a case like this, the soil is pushing the wall, and in this case, the tension side is going to be inside, correct? So if I need to put here reinforcement, I'm going to put it mainly in the inside face, not the outside face of the wall. This here called a retaining wall, but this retaining wall, the structure system, is going to be like simply supported beam, right? In the top, you're going to have this first floor is going to be resisting the movement, and the bottom, you're going to have the foundation and the concrete slab and grade to resist it. Now, I want to compare it to this retaining wall. This retaining wall, there is not here to restrain the top of the wall. So the pressures come from this side, and this works as a cantilever system. This one here, as you see this, you're gonna have a support. So this works here as a support, and this gonna be also a support. So this is gonna be like a simply supported like beam, and the force is gonna be coming from outside, and you should be able to model the stress coming from the soil like this. The one that you're gonna see a lot, I mean, that you can see even while you're walking in the street, you can see lots of these walls. Sometimes they're made out of reinforced concrete. In other cases, which is gonna I'm gonna say here, most of the cases gonna be out of block wall, like semi or cinder block, if you like. Some examples for some concrete retaining walls made out of concrete, not very common, because in this also precast, prefab. Sometimes you see this, but most likely it's gonna be masonry. I'm looking for some picture for masonry wall, but you don't really need a picture because all what you need to do is just walk in the street. You're gonna see plenty of them everywhere. So I'm gonna say here the types of wall I have. I have gravity walls. It's gonna be supporting vertical loads only, mainly. I'm gonna have also shear walls. It's gonna be supporting gravity loads, and you're gonna have also seismic forces like lateral forces on them. And then I have retaining walls, which retains the soil, like in this case. A basement wall is gonna be also a retaining wall, or one of these cantilever retaining walls, if you like. This picture here is taken from the ACI. They tell you here that this is gonna be structural wall. You don't here differentiate between gravity and shear wall. Differentiation is gonna happen when it comes to the design guidelines. When you do any wall design, whether it's gonna be designed for gravity loads or seismic loads only, or gravity and seismic loads, or even soil pressure like a retaining wall, you need to find the following 3 equations, right? If you have an axial load, this is gonna be the demand. So I'm gonna put this here to be your demand, right? You need to have a capacity to be greater than the demand. Strength, we call this a strength. We call those capacity. How about the demand? Do we have other names for the demand? Can someone help me here with this? What else? Demand ultimate or what? Yes, ultimate or demand. Anything else?
Design.
Yeah, factor, design. Yeah, so you can call this design axial load, design moment, design shear. So usually P is gonna be for axial load, M is gonna be for moment, and shear is gonna be V, right? We use V for the shear. So any case, you really need to have a greater capacity than the demand, whether we are talking about axial load, a moment, or a shear. You cannot get away with the wall, and the wall, let's say, is going to be deficient and resistant to axial load, and you have lots of axial load that goes to it. And you say now, as long as the moment is good and the shear is good, I don't really care about the axial load. It's not going to work this way, right? So now the reinforcement ratio, we have certain terms here that I need to define for you guys. What is this vertical reinforcement ratio? I'm going to say, let's look here at our shear wall that we're talking about. So I need to put the one with the shear wall. Like in this one, that was one example, right? And here's the shear wall section. So this is a section looking down. This is like plan view. So when it comes to the vertical shear ratio, what you need to do is to look at all of the rebars, total cross-section area of all of the vertical rebars, divided by the total cross-section area of the wall. You say, okay, this is here what I call rho sub L. L means, this or stands for longitudinal, which is the same as rho sub V. It is very common when you look at the code, you're going to see this rho sub L, not rho sub V. So for me to understand which one the longitudinal direction, I'm going to say it's going to be the vertical direction. How do you find out this ratio? I'm going to say it's going to be AS of the vertical rebars divided by the cross section area of the shear wall or the structure wall, let's say. So in this case, this steer ratio, it is going to be unitless because it's going to be square inches by square inches. So actually there is no units for this one, right? This is going to be rho sub L. Horizontal steer ratio is going to be equal to the cross-section area of the horizontal steel divided by the cross-section area in that direction. So in this case, I'm going to be taking this. You see this shear wall reinforcement, horizontal reinforcing. I'm going to be taking this and this, right? I'm going to be adding it as if I'm taking a section throughout the wall. Let me put here a section throughout the wall, right? And then after that, I'm going to be looking, let's say, in this direction, right? You're looking this way, and also looking this way. And then you figure out how many rebars that you have cut through, which is this horizontal rebars, right? And then you add them up all together, and then you divide by the cross-section area that you're cutting through, which is the wall height multiplied by the wall thickness. Are we clear on this? This cross-section area of the wall is going to be equal to the wall thickness divided by the height. So here's the wall height, right? You can see it's going to be the wall height, it's going to be the wall thickness. You're going to see lots of rebars here. You figure out how much is the total cross-section area for the 3 bars divided by the cross-section area in the horizontal direction. This one here, when this A sub G, this is going to be different because this A sub G, it is going to be like in plan view when you look at the wall section, like in this case here, right? It's going to be the wall thickness multiplied by the wall length. So this A sub G, it's not going to be the same as this A sub G. You need to be clear on this. Any questions?
Can you go over that again, Professor?
What I'm saying is this A sub G, it is not the same as this A sub G. This is going to be the cross section area, but in plan. So I'm going to say this is going to be like in plan view. And this A sub G, in this case, it is going to be what? I'm going to say not the elevation, it's going to be inside view of the wall, which means this is going to be equal to T of the wall. What is TW? Anyone can figure out what is T sub W?
Thickness?
The thickness?
Wall thickness, right? Multiplied by the wall height. I'm going to say HW, the height of the wall. How about here? What should I use? I'm going to say in plain view, this cross section area is going to be equal to T wall multiplied by the length of the wall. Because you're looking down at the wall, right? Are we clear on this? We're not really. Here's the length of the wall multiplied by the thickness when you do the vertical steer ratio. But if you're going to be cutting a section this way, right? The cross section area is going to be equal to the height multiplied by the thickness because you're looking at the section like this. And this gives you the wall thickness perpendicular to the screen. Okay.
Thank you.
The code here comes and then he says, they give you this table, and they're going to say, here's the minimum reinforcement. This regardless of the strength. So you see this table here? This is disregarding the strength of the wall, which means, let's say that you satisfy this already. Now you'd like to put the steer ratio, right? You'd like to put some reinforcing. So you have minimum values that you cannot go below, right? And it says here, this is going to be the minimum reinforcement for walls in plan, right? And then it says when V sub U, what is V sub U? What is V? Anyone knows what is V stands for?
Shear.
It's going to be the shear, right? When the shear demand is less than 50% of the shear capacity. So I'm going to say, well, code doesn't say it's going to be like gravity walls, but by definition, once you're going to have very low amount of shear compared to the capacity, I'm going to call it here gravity walls. So for the code, decode this structure wall, right? But as I said, for the structure walls, if the shear demand is going to be lower than 50% of the shear capacity, they're going to have separate, I'm going to say here, design provisions for it. So I'm going to say for this design provisions, I'm going to call this going to be design provisions for gravity wall. So I prefer to call gravity wall just to be sure that we understand what's going on. If the amount of shear demand on the wall is going to be low, I'm going to have separate design guidelines and procedure to work with it, right? And here's the first thing. They say, here's the minimum longitudinal reinforcement, which is vertical. Code doesn't include this V, so I decided to put here this V. Transverse means the horizontal is going to be root up T, which is the horizontal reinforcing. And they say, if the wall is going to be cast in place, which is going to be most of the walls, not precast, is going to be mainly cast in place. If you have deformed bars, which is the regular bars that you work with, we call deformed bars, not welded wire. Welded wire is going to be very thin, it's going to be very thin rebars, and is mainly used for slabs, let's say slab on grade, if you're doing a residential project, and you'd like to go to a cheaper option, you may go with this welded wire. But even so now, for any small residential, people use number 3 and number 4 bars. They don't really use this welded wire mesh, which is this welded wire reinforcement. So I'm going to say, if the bar size is going to be smaller than number 5, and if the bar size is going to be greater than number 5, and the yield strength, let's say, I'm going to say 60 KSI. Minimum vertical shear ratio is going to be 0.0012. And minimum horizontal is going to be 0.002. Look at this. If you're going to be going with any other rebars, which is not expected, right? Because most likely you're going to go with grade 60. In the past, we used to have grade 60 and grade 40. Nowadays, you don't really see grade 40. I mean, it is not out there in the market, but you're going to see it maybe in some old construction. So most likely we're going to be working with these two numbers. If I have a gravity wall, I'm going to say the minimum vertical shear ratio is going to be 0.0012, and minimum transverse reinforcement, which means horizontal reinforcement, is going to be 0.002. So I have here two numbers to work with. If I'm going to be going with any rebars more than number 5, I'm going to be using these two values. So if the rebar size is going to be more than number 5, this is going to be the minimum. Now, does it mean that I still need to do the strength check? All of these checks? I'm going to say yes. But this is going to be the minimum amount of rebars that you can put in a wall as a gravity wall, not as a shear wall. Because I'm going to show you here a different table. Once the reinforcement, right? Once the shear, which is this V sub U, is going to be more than 50% of the capacity, you're going to have different values. Actually, it's going to be jumping up to 0.005. We're going to see this later. But now you need to understand that the code first says, I'm going to call it here a structure wall. I don't have this thing as gravity and shear, but once the shear demand is going to be less than 50%, I'm going to have a special treatment for it. And this is what I call here a gravity wall, like in the past. Now the spacing of the rebars. Longitudinal rebars means vertical. So I decided here to put V because it's kind of confusing. Someone's going to say, when I'm looking here at this shear wall, right? Here's the shear wall, right? Now where is the longitudinal? So it's going to say, this can be the long direction of the wall. This looks like to be the longitudinal direction of the wall. You can see, no, this is going to be the longitudinal, and this is what you call here transverse. It's kind of confusing, isn't it? So I decide here that every time I see a definition or discussion on longitudinal, I'm going to put V next to it, and once it says transverse, I'm going to put H. So we're not confused about it. We don't need to discuss it again. So I'm going to say, okay. When it comes to the spacing of the vertical rebars, it says the spacing is going to be the smaller of. This is going to be the maximum spacing, right? It's going to be 18 inches or 3 times H. What is H? Is H the wall thickness or the wall height? We're going to say H is going to be the wall thickness. Which wall thickness? I'm going to say here, like in this case, it's going to be the wall thickness. I'm going to say this is going to be H from here to there. From this point to this point. Total thickness of the wall. I'm going to call it here H. Right? Anyone recalls what other symbol I've used for this H? I used before TW, right? Which is the wall thickness from here to where I'm going to call it here the wall thickness. But in the code in this section, this says H. I said fine. And here they call it H, but usually we prefer to call it T sub W. What's T sub W again? Wall thickness, which is the same as H. But if you say H sub W, it's going to be the total height of the wall. So, okay. So the spacing here, you cannot, let's say, you cannot just have the same reinforcing bars and satisfy the requirements of this section, and you satisfy the requirements of the trench, and then you put the bar spacing, let's say, to be at 4 feet on center. Now you're going to see lots of cracks in the wall. This is not good. So you'd like to have it closed. So to have it closed spacing, I'm going to go here to a maximum of 18 inch. So you cannot go beyond 18 inch. So in any wall, you cannot go beyond 18 inch. So if you see a wall here with a spacing at 20 inch, you say that something is wrong because it's not following the code. It's the maximum of 18. So does it mean that 16 inch is a good answer? I'm going to say yes. 16 inch, 14 inch, 10 inch, right? Maybe 9 inch, 8 inch is going to be okay. But you don't try to go more than 18 inches. And if the wall thickness, let's say, is going to be 8 inches, let's just imagine the wall thickness is going to be 8 inch. What's going to be the spacing now? Yes, they say the spacing is going to be either 24 inch or 18 inch, the smaller of the two. So based on the wall thickness, and if you have a wall, 8 inch wall, what's going to happen? Let's say with an 8 inch wall, it's going to be 24 inch, but also I have condition here to be 18 inch, so I'm going to follow the 18 inch. And then you have here more discussion on if the wall is going to be 10 inch or so, what's going to happen? You need to have 2 layers of reinforcing bars. So I'm going to take you back here to our picture. I have here 2 layers of rebars. And the code says, if you have a wall 8 inch or thicker, you really need to have 2 layers of rebars. Meaning, if you have an 8 inch thick wall, you can have 1 layer in the middle. You don't really need to have 2 layers, right? In this picture, I'm showing here 2 layers of the rebars in both directions. The code says this is true. You really need to have 2 layers of rebars, right? In each direction, only when the wall thickness is going to be 10 inch or larger. It's going to be a must. If the wall is 8 inch, you can go with only 1 layer in the middle. It's going to be okay. The spacing of transverse reinforcement. You see the spacing, look at this. The spacing is going to be what? Shall not exceed what? 3H and 18 inch. What's the difference between this and this? You see the difference is this is going to be only, right? For horizontal rebars, it's going to be the only 2 conditions, 3H and 18 inch. Here, you're going to have a little bit of more discussion, right? But it is mainly the same. It's going to be 3H or 18 inch. And usually people, when they do an actual design, they'd like to go 16 inch. 16 inch is going to be very common. This is what you're going to see. Because 16 inch works in masonry and works in reinforced concrete. So people just tend to say, let me just go here with 16 inch, easy number, I'm going to be satisfying all the code requirements, and also it's going to be add some strength to my wall. So, okay, now let's see an example. Ready for example or not yet? Are you guys there? All right. So in this example, it says 18 inch thick concrete wall. It doesn't say shear, it doesn't say gravity, but it says designed to support gravity loads only. So I'm going to say gravity load only, which means the shear is almost nothing. So I guess I'm going to be following within this table, right? This table is going to be guiding me, controlling my design. It says the minimum vertical reinforcement, ASTM, A615, grade 60. So I know now yield difference is going to be 6 KSI. And say to be used is, and the horizontal rebars. And then they give me 4 different reinforcing programs or options. Yeah, say, let me check. One of the conditions, it says, when the wall thickness is going to be 10 inch or larger, you need to go with 2 layers. And this is true because it says here each face. So each face of the wall, you're going to see here number 5, and the space is going to be 12 inches. Let's say, let me go back here to this guy. No, this is not the one. To shear walls, right? It says each face, so it's going to be face of the wall. So in this case, you see this rebar, and this rebar is going to be vertical rebars. I have 1 rebar at each face. So if the distance from here to there is going to be 12 inches, like in this case, and I have number 5, it means I have number 5 at 12 inch each face, which means that you need to double it. When you do your analysis, you need to multiply by 2 because it says here each face. How about the design loads? I'm looking here for design loads because I'd like also to work on this issue. And I don't see anything about the strength of the wall needed. It just says, what's the minimum reinforcement ratio that, or the reinforcement that you can go with? So Yes, okay. Here are the two values. Do I have number 5 and less, or anything like more than number 5? Yes, say, no, I have different. I have options. I have number 5, I have number 6, number 7, and number 5. Okay, so which one do you think I'm going to go with? Let's say that number 5 at 12 is good and also number 6 at 12 is good. Which one would I go with? So I'm going to be going with the one that's going to give me the minimum reinforcement, the smaller amount, because it's going to be cheaper, right? That's okay. For number 5, if I have number 5, it's going to be 60. The vertical is going to be 0.0012. But if you go to number 6, you need more reinforcement ratio. It's going to be 0.0015. So I said, okay, now I understand. And here's the two values for the horizontal, 0.002 and 0.0025. Okay, good. Let me check this out. How much reinforcement are we providing here? Because what I'm trying to do is to find out this reinforcement ratio. This is going to be what I'm trying to do here. That's okay. What does it mean by number 5 at 12, each face? EF means each face, all right? One number 5, it has a cross-section area of 0.31. So you see, what is that? This is going to be AB for number what? 5. One rebar, it has a cross-section area of 0.31. Why do I have this two? I have this two because I have each face, two faces, right? It says here each face, so I need to multiply here by 2 because I have 2 rebars. I'm gonna say, where's the spacing? I'm gonna say here's the spacing. Look, it's gonna be this number here of the rebar. And what is that? Because I'd like at the end that my answer is gonna be as in a square inch per foot. So if this is gonna be your wall, right? You can see here's the wall. What I'm trying to do, I'm trying to take here a foot of the wall. So the length here is gonna be a foot from this point to that point. And I wanna see how many square inches of the rebars that I have within this 1 foot. You see the distance from here to here is gonna be how much in this case? Let's say this is gonna be 12 inches. Okay. Now let me think again about the analysis. As it says here, I have 2 bars, 2 vertical rebars. Number 5 is gonna be 0.31 times 2. I'm gonna multiply here by, first I'm gonna divide by 12. When you divide here by 12, which is the spacing, now you have the cross-section area of the steel as in a square inch per inch. So for now, just disregard this. Just try to understand what's going on. If you take 2 times 0.31, it means the cross-section area of 2 rebars. These 2 rebars, right? Now divided by 12 inches, which is the spacing. You see from here to there, let's say it's gonna be 12 inches. As if you're taking this rebar and you're making it flat. You're making it something like this, very thin. And then you come back and then you say for each 1 inch of the wall length, how much is A sub S in this location here? So you say in this case, I'm gonna be taking here 2 times 0.31, total cross-section area on both sides of the wall, divide by 12, it's gonna be here square inch per inch. Now I'd like to have it as square inch per foot, yes.
So I see that you said it's 12 inches. Is this the same thing as when we learned that in California it should only be 6 inches apart?
Yeah, but this is for a different thing. This is gonna be for columns, right?
Oh, okay. Thank you.
Yeah, but this for walls. But you are correct. So again, here's the wall section, and they have a bar right here. So you see, here's 1 bar. Right? Another set of bars. And the third set of bars. Let's say for now, for a second, that the spacing from here, right? The typical spacing from a bar to a bar, I'm gonna put it here to be 18 inch. All right? Distance from here to there is gonna be 18 inch. meaning the distance from here to there, from the center to the center, right? It's gonna be how much? Someone help me here. The spacing, we're gonna say this spacing is equal to 18 inches, okay? Which is this distance here. Good. Now, take the cross-section area of these two rebars, all right? Divide by this distance. So if you take this, it's gonna be what? Square inches. Divide by this, it's gonna be square inch per inch. Per inch of what? Of the wall length. Again, as if I'm taking this rebar, I'm gonna be hitting on it and make it like a very flat, a very thin piece of metal here, right? You guys see what I'm trying to do? So this two rebars, I'm gonna be taking in, let's say I'm gonna be melting them. Now it's gonna be melted, right? I'm gonna be creating a very thin plate. Now I'm gonna be taking here 1 inch of the wall length and see how much steel that I have within this 1 inch. Now, how do you do this mathematically? You take two rebars, 2 times 0.31, like what you see here, divide by 18 inch, which is the spacing. You say, now I'd like to see it for a foot. So what do you need to do? Apply by this 12. So at the end, this reinforcement is gonna be 0.62. Let's say in this case, inches square per foot. Now let's look at this. Number 5 at 12. You see, here's the spacing. You divide by the spacing, right? And then multiply by 12. This 12 is gonna be constant because you'd like to see this as per foot. So it's gonna be 2 times 0.31 times 12, because you'd like to see it per foot, divide by 12, which is the spacing. How about in here, number 6 at 8 inches? Look at number 6. For number 6, cross-section area of one rebar is gonna be 0.44 times 2, because you have two rebars. You divide this by 8 inches, because the spacing is gonna be 8 inches, and then multiply by 12. Same thing here for number 7 at 12, number 5 at 18. At the end, this is gonna be the amount of reinforcement that you have here for each option. Now, which one is the largest? Look at this. Yes, say the largest is gonna be this, number 6 at 8, right? It's gonna be too much. Now, which one that follows it? I'm gonna say 1.2, and then 0.62, and then 0.41. If I'd like here to check my choice, of course, is gonna be number 5 at 18. If I can go to number 5 at 18, it's gonna be the cheapest option. This is gonna be our best guess. Any questions on this? You guys understand how do you do this analysis or this calculation? Yes?
Professor, what does EF mean?
What?
What does EF mean?
EF, good question. Each face. You see this? We say that you have two faces, right?
Right. Yeah, got it.
Okay. Also, sometimes you see here, each way, each face. Like in here. What is this EW? It means each way. Each way means vertical, horizontal. Each face is gonna be EF. So sometimes people draw it EF, EW. So you know that this is gonna be each face, each way, you know. All right. So definitely I'd like to use this if possible, right? Because it's gonna give me here the smallest amount of reinforcing. Yes, say if I'd like here to go with number 5, because I have number 5, number 6, and number 7, I'm gonna go back here to my table. For number 5, my minimum is gonna be 0.0012. For number 5 and larger, it's gonna be 0.0015. So okay. What does it mean by 0.0012? How much of a steel are we talking about? You say if I have number 5, which means option A or option D, the minimum A is vertical based on this is going to be equal to 0.0012 times 18 inch. What is 18 inch? I'm going to say the wall thickness. T of the wall, right? Times 12. What's 12? This is going to be the foot that we were talking about, right? We said that I'd like to have it per foot. So I'm going to say here per foot. So I'm taking here 12 inch of the wall length. So what I did, I've taken the wall thickness by 12 inches, multiplied by 0.0012, so that I know how much steel is needed as in per square inch per foot. I run the analysis, it gives me here 0.26. So the minimum is 0.26. Now, which one do you think can satisfy this requirement? You can say any one of them. All of them, they cover it. Now, which one is going to be your choice? I'm going to say number 5 at 18. Why? Because number 5 at 18 here is going to be okay if I want to use it. I have enough reinforcement and I have good spacing. Look at the spacing, 18-inch. This satisfies also the spacing requirement. Look at the spacing requirement, 18-inch or 3-inch. H is gonna be 18-inch times 3 is gonna be too much, so I don't really care about this. I know that 18-inch is gonna be controlling the spacing in my design. So I'm gonna say in this case, answer D is gonna be okay. Number 5 at 18-inch is gonna be good. I don't see here a problem with this for the vertical reinforcement. How about if I'd like to go here with number 6 and number 7? I'm gonna say, yeah, do you want to try it? This step is not really critical, and I shouldn't be spending my time because I know that number 5 is the lowest cross-section area. Is gonna be the cheapest option, right? It's gonna be the more cost-effective option, if you like. And I know that I was able to satisfy them and done. But I'm saying here, let me just entertain this idea. What would happen if I use here number 6 and number 7? I'm gonna say here rho L minimum. Let's go back here to our table. It's gonna be 0.0015. 0.0015, right? Meaning what? Times 18-inch, which is the wall thickness, times 12-inch for the length, 12-inch of the wall. I have here 0.324. So I'm gonna say, look what happened. The minimum needed, if you're gonna be going here with number 5, is gonna be 0.26, but the minimum needed, if you're gonna go with number 6 or 7, is gonna be 0.324, and that's here that number 5 is good enough. So I'm just gonna be going with this. Okay, give me a second, please. So this is gonna be my choice here. I'm gonna be going here, as you see, with option D because this is gonna be the cheapest option. So this is where you can save in the amount of steel that you put in the concrete. This is okay. How about the horizontal reinforcement? I'm gonna say horizontal reinforcement. It seems that I have the same distribution because look at this. Same reinforcing program, number 5 at 12 each face, number 6 at 8, right? Number 7 at 12, number 5 at 18, exactly same, right? So I'm gonna try this also for the horizontal reinforcement, but look, before we continue, I need to look at the minimum reinforcement needed, right, for the horizontal reinforcement. It's gonna be 0.002 and 0.0025, depends on the bar size. So okay, let me be ready for it. I'm gonna say 0.002 for number 5 and 0.0025 for number 7. So what does mean by 0.002? Take this steel ratio, the minimum required, multiply by the wall thickness, multiply by 12-inch, which means 1 foot of the wall length. You need here 0.432, right? And if you are going to be going here with number 6 or 7, you need 0.0025, meaning how much? 0.54 square inch per foot. Now let me see here. This is going to be the same analysis I've done here, right? Exactly same numbers, horizontal and vertical, the available options. So I'm going to say, if I'd like here to go with number 5, I need minimum of 0.432. Would that be okay? I'd like to start from the bottom because it's going to be the smallest amount of reinforcing. You see, this is not good, right? Because if you're going to be going here with option D, you're not providing enough reinforcing to cover the minimum. But if you still want to go with the lowest, right, and then you go a little bit higher than this, going to be going here with 0.62, compare 0.62 to 0.432, it seems that I can cover it here with number 5 at 12. Meaning, number 5 at 12 is going to be a good option, it's going to be a good solution. Therefore, at the end of the day, for this wall, I can go with number 5 at 18 for the vertical, and when it comes to horizontal, I'm going to be going here with number 5 at 12, just to satisfy the minimum reinforcement needed per code. Any questions before we move to second example?
Professor, so the P of T just represents the ratio of steel? Or could you explain that?
Yeah, this ratio, steel ratio. Okay, good question. Did you see this before? This is going to be the horizontal steel ratio. It's called rho sub T. And this rho sub T, T stands for transverse. So when you go through the code, you're going to see the code here transverse. We'd like to call it horizontal because for us, we have horizontal and vertical. It's going to be too easy. I'm going to say here terms that we use when it comes to our analysis.
Okay, thanks.
No problem. All right, now I'm done with the first example. I'm going to be looking here at second example. It says 8-inch thick reinforced concrete wall. Dead load is 5 kip per foot. What's keep a linear foot, meaning here's the wall, right? This is like an elevation. So let me write this could be my elevation. It's not good when you write with this color here. Yeah, see, this give you my elevation. Looking at the wall. And they have a uniform load applied on it as an axial load. So we're gonna have some loads coming this way, right? Like vertical load. Arrows are not the same. This is the best we can do with the software. You're gonna have uniform load acting like this on the wall. Are you guys following me? Yes? Yeah?
Yes.
Yeah.
Okay, great. How much is this uniform load? As a vertical axial load? 5 kip per linear foot as a dead load. So for each foot, if I'm going to be taking here a foot, if this length of this strip is going to be a foot, I have 5 kips here. As a dead load, and live load is going to be 3 kip per linear foot. So I'm going to say, how about the ultimate load? Someone can help me here with the ultimate load. I'm going to say W ultimate equals to how much?
1.2.
1.2 what?
1.2 dead load plus 1.6 live load.
Like, how much is the dead load?
5.
Plus 1.6 times what?
3.
How much is this?
10.8.
10.8. What units?
Keep per foot.
Kip per foot of the wall length. Okay, good. Concrete strength, 2500 psi. Reinforcing steel, grade 60. It says select the vertical reinforcing needed for this one. So it's going to be based here on what? It's going to be based on the strength. Now, is this the only equation I need to run, or do I have another equation? Do you have another equation for gravity? Load
So
combination
1.4 dead load.
times 5. How much is this?
7.
I guess this one controls, but I need to show answers, right? Now I know that I'm going to be using one of this equation, the one for tight columns. I say, okay, let me look here at, oh, this is not 1.3. How come? See this number here? This is wrong. Should have been 1.4. Am I correct? Yeah, 1.4. And this one should have been what? 7. Okay, perfect. Where does this 1.3 come from? Weird number. So anyways, this is going to be the one that controls my design. This is going to be 10.8 kip per linear foot. If you're talking here about 1 foot of the wall, so I'm going to be taking this 1 foot of the wall, just 1 foot. The wall thickness perpendicular to the screen is going to be 8 inches. So the gross section area is going to be equal to 8 times 12. What is 8? You can see here is going to be the wall thickness, right? T wall. And this 12-inch is going to be the segment of the wall that you're taking here to study. So it's going to be 96 square inches. Your minimum reinforcement, if you are planning to use here number 5, don't forget here I'm trying to use here number 5, is going to be 0.0012. How do I know this? I'm going to go back here to my table. It says here minimum reinforcement, vertical reinforcement ratio is going to be 0.0012. When I have rebar number 5 or smaller, I'm planning here to use number 5. It's very convenient when you use number 5. Easy to bend, easy to fabricate and work with. You see here, here's the 0.0012. It means that I need at least 0.115 square inches. I'm sure that you're going to say per foot, correct? Because the whole thing here is going to be per foot. I'm taking here 12 inch. It's going to be per foot. And the maximum spacing is going to be 3 times the thickness. This is going to be 8 inch, 24 inch, or 18 inch. The smaller of the two. So I'm going to say, I'd like to go with this, if possible. I'd like to try number 5 at 18 because it's going to be the cheapest option. So, okay, let me try here number 5 at 18. Here's number 5. This is going to be what? AB for number 5. You remember 0.31? 12 inch is going to be this 12 inches, the length of the wall, and 18 inch is going to be what? The spacing. Did you guys hear me? This 12 inch is going to be the length of the wall. Am I correct? Yes. Because I'd like to have it at the end per foot. Like here, that's one also. Someone's going to say, well, maybe we should have put units here to be square inches per foot. I'm going to say, yeah, why not? But we know that the whole thing here is done per foot because my cross-section area was here as a per foot. So when you take this cross-section area, multiply by unitless factor, you're going to be getting square inches. But we know the whole analysis is made for a foot long of this wall. Now, the needed based on this code is going to be 0.115. The provided, if you like, goes number 5 at 18 is going to be 0.206. Is this a good design? Yes, say a good design. Yes, because what you have provided here is more than the minimum. You can say, how about the capacity? I give you here this ultimate load. Where did you use? Did you use it yet? I'm going to say no, it should be coming, right? So let me look here at the capacity of the strength. So the first check I did here, I tried to start with the minimum amount of reinforcement I can possibly use, right? I don't want to start with something to satisfy the requirements, which means the strength, and then come back and check it versus the minimum. I'd rather start with the minimum, throw the minimum usually in each wall I'm going to be working with, and then confirm the capacity of it. So, okay, this is going to be my choice, number 5 at 18. This is going to be the first choice. Why? Because it's going to be the smallest amount of reinforcement to cover the minimum reinforcement ratio, 0.0012. Okay, now how much is AS for this? I'm going to say cross-section area is going to be 0.206. We have just done it here, right? How about VPN? You can say, okay, let me now do that for the type count. The phi factor is going to be 0.65. We have done this before a few times, so we know this. 0.8 is going to be this constant. What is this constant for? I'm going to say this is going to be for the small eccentricity thing. 0.85 F prime C, 2.5 KSI, right? Cross-section area is going to be 96. Where is this coming from? Okay. Let me look at this. A cross-section area, 96 square inches. The wall thickness multiplied by just 1 foot. We're going to say this is going to be what? The 96 inches. How about the steel? How much steel are you putting? I'm going to say the amount of steel I put there is going to be this amount. It's going to be the actual steel. You're not going to be using the minimum because I ended up by providing 0.206. This is going to be the actual amount that I'm going to plan to put in there. Plus 60 F sub Y times AST. PPN, which means the capacity of this wall, is 112.3 kPa foot. How much is your demand? You remember the demand? That was the demand, right? The 10.8 that we have done here. Look at this, 112 versus 10.8. Yeah, plenty of capacity. This is actually very common. When it comes to reinforced concrete wall, or it's going to be gravity wall or shear wall, you usually have lots of capacity in axial load forces. So when it comes to axial load, you have plenty of capacity, and you shouldn't have a problem. And use the minimum reinforcement to be able to make it with you. Unless you have many stories, right? It's going to be different subject. Any questions?
I have a question about the spacing between the rebars. If you
Yes.
go back one slide.
Yes.
So the max spacing of the vertical rebars. So the max spacing, you're referring to the spacing between the center of the rebar to the next one?
Yes, like in here. You see, like the center from here to here.
Mm-hmm.
Or like in the other picture, which is this one here. With the spacing from one rebar, which is this guy. You see this 18-inch max?
Yeah.
This is the one I'm talking about.
And then the 18-inch maximum, that's according to code, is that right?
Yes, yeah, you have 2 limits
Okay.
for the code. Code says here, I have 2 limits that you need to worry about for the horizontal and the vertical. The first one here is going to be for the vertical. It says, shall not exceed, this gave you the spacing, right? Shall not exceed the lesser of, which means the smaller of the 2. So I have here 2 conditions. One of them say 3 times h, the wall thickness, and 18 inches. Now let's see how that was treated. Yes, say in here, the wall thickness is 8 inches, right?
Mhm.
3 times 8 is going to be equal to 24 inches. And
Yeah.
the other condition, according to the code, also is going to be 18 inches. So you need to take the smaller of the two. So in this case,
Okay.
I'm going to be using this, right? 18 inch. So I cannot go to 20 inch, for example, right? 20 inches is going to be bad because you are not really following the code. You need to go to a maximum of 18 inch, which means 16 inch is good, 14 inch is good. So that's why the code.
Okay.
Right? Thank you.
And to find the our minimum cross section of our rebars, the number 0.0012, that one we refer to the yeah,
This
right
table.
here.
Yeah.
Okay.
So
Will
first
we
you need,
always
yeah, go ahead.
will we always be working with the looking at the section that pertains to the deformed bars?
Yes, we don't really use this welded wire. And for this art course, I'm not going to be using any other thing. And also in practice, this is going to be the one that you use in walls. No one would ever use welded wire reinforcing in a wall unless this wall is not really structural wall. In practice,
Okay.
we just use the foam bars.
All right, thank you.
No problem.
So when we do the calculation, let's say we get the capacity to be greater than 50%.
Oh, you mean for this?
The one we did earlier, the last example. Yeah. So
Like this check for the shear.
mhm.
If you recall here, it says they give you your dead load and life load. Did you see any shear forces?
No.
Okay, so in this case, what's the conclusion? I'm gonna say conclusion is gonna be that simple. I don't have shear demand. So it is true that V sub U is gonna be less than 0.5 for VVC. So in this case, I'm gonna say yes, this table is the table I can use in my analysis.
Okay, thank you.
Okay. Let me look here at shear wall section and let's see the minimum. I just want you guys to see this. For the shear wall reinforcement, it says row minimum in both directions. Vertical, horizontal is gonna be 0.0025. So it's gonna be for longitudinal and transverse. It's gonna be 0.0025. Just one value. Now they make it simple for us here. So come to shear walls. But in this case, you're gonna see here some good amount of shear wall, right? If you really wanna use this, look at this vertical steer ratio or horizontal is gonna be 0.0025. So in here, you see the values? You have different values because just gravity load. So it's not really stressed. I mean, the wall just exposed to some vertical loads. But in here, our wall is going to be exposed to lots of lateral forces, seismic forces. So it's going to be a kind of a little bit more important wall, if you like. That's why you put more reinforcement in the wall. All right. Now, in the retaining wall, what happened? You have the front slide set. It's going to be number 18. And now we're going to have an assignment, right? Like for the project. And I'm not going to be asking for you guys to return it on Wednesday, and instead it's going to be Sunday. Because you're going to have, and instead of asking you to turn it back or submit it on this coming Wednesday, I'd rather just keep it to the end of the time off of your holidays. Are we good about this? Everybody's hearing me?
Is this the Sunday after Thanksgiving?
Yes, Sunday after Thanksgiving. Absolutely.
So just to be sure, the 29, correct?
This is correct, 29. Yes, it's going to be
Okay, thank
29.
you.
Right. So we're going to have a peaceful week. So you don't really have to work in the middle of it. You just keep it to the end. Okay, so I'm going to give you something very simple. It shouldn't be tough. We're coming here close to the end of the semester, and we'll see what's going to happen in your final. So in retaining walls, as we have discussed, we have this type, which we call here a cantilever system, because the way it works here, you just assume there's going to be like a vertical member, and then you have lots of pressure coming this way. The soil pressure is coming like triangular distribution. Have you guys taken this soil pressure distribution? Did you guys take soil mechanics? Anyone has not taken soil mechanics class? I'd like to hear from you.
I'm taking it right now.
Okay. Do you take the soil pressure distribution?
I think so.
Okay. You know the difference between active and passive soil pressure?
No.
So what did you take about soil pressure? Can you?
No, I don't think we've covered it actually.
So you're not taking in soil pressure? You have not taken lateral soil pressure?
I don't think so.
Okay.
I'm just now taking that in foundations.
You are taking this in foundation, but you have not taken in soil mechanics, right?
No, we didn't go over that in soil mechanics.
Okay. All right. The issue is so simple. If you want to understand it, let's say that you have a wall like this, so that we understand the difference between the two. If you have a cantilever wall, you start to push it, I'm sure that the wall's gonna rotate a little bit. So this AB is gonna be before rotation, and A prime B is gonna be after rotation, right? So you push against the wall, and then the wall's gonna be moved a little bit. So what do you expect? Don't you expect to see maybe some cracks here on the top of the soil? Right? Why? Because soil cannot take any tension. When this point moves from A to A prime, what's gonna happen to the soil here? Right? This length from C prime to A is gonna get larger, right? You see the length? First, it was up to here, this distance, now you extend it. So what does it mean? It means that the soil is not pushing anymore. Why? Because once you start to form some cracks here, the soil is gonna be stopped pushing. Now we have another thing that's gonna be called here passive pressure. Passive pressure is gonna happen when you start to push against the wall like this. Now you're gonna move from A to A double prime. So what happens? You are pushing against the soil. So what do you expect from the soil? The soil here is gonna be pushing harder. So the amount of horizontal pressure that you develop in a passive pressure situation, which means when you push against the wall with some means, is gonna be completely different from that case. So in this case, the pressure is gonna be lower. In this case, the pressure is gonna be higher. How about when you have a rest condition? What is that rest condition? A rest condition is gonna happen when you have a basement wall, which means that you have a floor system right here, and then you have foundation system right here. So you're not really pushing against the wall, and the wall is not really moving because the building is solid, right? This building is not going anywhere, correct? From this soil pressure. So the building is gonna be staying there. This is why we call it at rest. So the highest pressure in the three cases, this is gonna be number one, this is gonna be number two, this is gonna be number three. Active pressure is gonna happen when you have a cantilever system. It's gonna be like this, right? This is a cantilever system. There's no concrete slab here, like a floor line. Or here, look at this case. It's like cantilever system. Look at this case. This is gonna be cantilever wall, right? Look at this case. This is all cantilever wall, right? And this, here's the wall, here's the footing. Similar to this case here, right? So what you call here cantilever system is gonna be what? Active pressure. This one is gonna be what? It's gonna be at rest. See this case? It's gonna be at rest. Why? Because you restrain the one on the top, you restrain to the foundation. So someone's gonna say, where is this one about the passive? I'm gonna say, you're not gonna see it here, but I can show it to you simply. If you think about this, you say, I'm pushing, this soil is pushing against the wall this way, right? So I'm gonna say, you have lots of pressure coming this way, correct? It's gonna be active. How about the soil on this side? Actually, the soil on this side, you are pushing against it. So in this side, you're gonna have your passive pressure, and this side, you're gonna have an active pressure. So here, I'm gonna say here, passive pressure. That's why we made it in blue, right? It's called passive, and this is gonna be the active. I'm happy, it's written here. So we're gonna have some active pressure coming here to push the wall, and the soil is gonna start to crack, and this is the pressure is gonna be smaller, kind of, like lower in value. And this passive pressure is gonna be high, is gonna be coming when you push this wall against the soil. Because the total amount of pressure that you have here is gonna be larger than this. The pressure intensity itself here is gonna be smaller, but the total pressure is big. So the wall is gonna start to move left. In this case, you're gonna see this soil here is gonna be exposed to pressure, so the intensity is gonna be high, but the amount of total pressure is gonna be lower than that for the active. Guess we're coming here to an end. You guys, you enjoy your time off, and you have a happy Thanksgiving to everyone.
Thank you, Professor.
Thank you. All right. Have a good one.
You too. Have a good one.
Okay. Bye.